Here we go. I will begin with a word of prayer. You got it? Okay. Dearly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today. Help us to, again, glorify you in what we do and just understand a little bit more about math today, Lord. In your name I pray, Lord Jesus. Amen. So here we go. I want to talk about the principle. I can't remember how to spell principle. That's not a good sign. There's two different principles. I can't remember which one of them. Curses. Where'd that thing gone to? Oh man, what's that? Oh, principal, nth root, function. But we're going to get to that. First of all, we're going to study what's the solution set. What is the solution set of think about this here. W equal z to the n. Right? Yep.
What's the word that starts with an R?
Root. It kind of looked like roof, though, didn't it? All right. Or maybe I should, you know what, well, yeah, fine. All right, so we want to solve w equals z to the n, where w and z are complex variables, all right? So here, we'll think of w as given. As a given, all right? We're thinking w as being given, z is a variable. We're trying to figure out what it could possibly be and get you back to w, all right? So, of course, w being given, we can write w is equal to, well, let's say, s e to the I beta. All right. So we can find a magnitude, like s is the modulus of w, right? And beta is, you know, some argument of w. All right. Now, z to the n, also, we'll let z equals to r e to the I theta. All right. So here again, we're gonna fix our choice of s and beta there. All right. So then what? Well, if we look at then what's z to the n? Well, z to the n is r e to the I theta raised to the n power. All right. Which is equal to r to the n, e to the I theta to the n power, but by de Moivre's theorem, which I can't say, but you can read, which you're going to prove in homework 1 anyway, right? So you get that. All right, so let's look at what we got. We have s e to the I beta equal to r to the n e to the I times n theta. Our goal right now is to describe all possible z which solve this equation for given w, all right? So in order for this equation to be true, what has to be true? Two things, right? Two things we get. On the one hand, s is equal to r to the power n. On the other hand, we need that e to the I beta is equal to e to the I times n theta. All right? In other words, for two complex quantities to be equal, they have to have the same direction and the same magnitude. Yeah? Now, s and r are real quantities. So we know how to solve that equation since, like, I don't know, 9th grade. Something like that. The solution to this is easy. right? We see what we get. We get r is equal to the nth root of s. And this right here is just plain real algebra. All right? So it's always the positive root because by assumption here s is the modulus and is therefore non-negative. All right? So there's no funny business there even. Just the positive nth root. On the other hand, the imaginary exponentials, there's some fine print here. What does this tell you? Remember, that means that cosine and the sine of those angles both match, right? So as we discussed last time, this would mean that like beta minus n theta is an element, well, it's equal to, let's say, 2 pi k for some k in the integers, right? So remember that the s and the beta are given. We're really trying to solve here for r. Well, we did that already. We solved for r. And now we're trying to solve for, for theta. So we can do that, yeah? Let's see here. Now, for the sake of specificity, let me suppose that beta is equal to the argument of w, the principal argument, namely the angle that's between, minus pi not included and pi included. All right, fine. So let's remove that ambiguity if you're worried about it, all right? All right, so then solve this for theta. What do we get? Theta is equal to, apparently, you know what, if you guys don't mind, I'm going to make a slight change of notation here. I'm basically just redefining k as minus k. No loss of generality there because, of course, it's just integer. But that just makes the formula nicer for me. Theta is equal to, well, beta plus 2 pi k over n. All right? Now, definition, if w is equal to z to the n, all right, then z is an element of the w to the 1 over n power. In other words, we say that the solution set of the equation w equals z to the n is the w equals 1 over n. That's the notation for the solution set, all right? It's going to be a set. We just found a characterization of the set over here. Let's write it out. So by this calculation right here, we see that we see that z has to be equal to what? Z has to be equal to the nth root of s, right? Times what? Times e to the I theta. But here theta is what? Apparently beta plus 2 pi k over n. For, k an element of z. This right here is a typical element in the nth roots of w. Let me just write that out. These are the nth roots of w. Yes, sir?
Just for clarity, when you say beta is equal to rw, the capital A in r means that we're taking the principal value, the one from negative pi to pi.
Yeah, negative pi not included. Yep, that is right. Now, we can do better. All right, what's a typical element look like? Well, let's simplify this a little bit, right? So z is equal to, well, first of all, I guess I can leave it as s, but what is s? It's really the modulus of w, right? That's what that was. And I'm going to write this as e to the I. Now, beta was what? Well, beta was arg w over n, all right? And sidebar, notice that e to the I beta over n plus 2 pi k over n by properties of the imaginary exponential, which, man, I'm glad you guys are doing homework. You will prove in the homework. You probably already got me, don't you?
Yeah.
Okay, cool. Sorry, I had some bad experiences the last couple of years with like substandard videographers because I was teaching to like really small classes, and like people stop caring about the video work when there's like 2 people in the class. So, where I was teaching in West Alabama before I came back, one semester, I had 10 students. That's total. I'm talking about in like 3 different classes. In one class, the most I had was, I think, what was it, 4? I don't know. It was it was University of West Alabama. I was in Alabama. You know, go back to my kin. Okay, that's a lie. Let's see here. I beta. I'm a Yankee. Not really, though. Who wants to live there? I 2 pi over n to the k power. So using the law of exponents for imaginary exponential, and again using de Moivre's theorem to break it, pull the k out, right? We can write that. And so keep in mind, of course, that this beta, like I just said a second ago, is arg w, right? So what I have written right here is what? It's just this part, right? So I still got this part over here. And so you're like, well, can you please introduce some more notation that we need to remember? Because that's really what we like about math courses, is learning new notation that are native to the course and no one else uses outside the course. Well, that's not entirely true. There's various notations for this, but here's one. Omega sub n equals to e to the 2 pi I over n. All right. Some books use like one of these deals. Sub n's, what's z, or I don't know what it is. Squiggle, yeah, zeta, okay, zeta. But I'll use omega. Oh, okay, omega sub n. And you notice what this is. This is omega sub n, all right, to the what? To the k power. Oh, definition. This right here is the principal nth root of unity. Oh, look, I remembered how to spell it now. I'm improving. Woohoo! Let me give her that. The principal nth root of unity. That's kind of arcane language. What's unity? I see someone saying 1. Yeah?
Yeah, just 1.
Just 1? Okay. Yep. This is correct. It is the number 1. I suppose in an abstract algebraic sense, it's the multiplicative identity of the algebra. All right. A unidal algebra is one which has such a thing. But anyway, it's the principal nth root of unity. Now, let's just take a minute to appreciate what that looks like for low n. And then I will come back to this calculation and say more about it, okay? So leave yourself some room to write some things, all right? And let's look at the nth roots of unity over here. Let's start out small. N equals to 2. What goes on there? What's omega sub 2 equal to? E to the 2 pi I over what? 2, also known as e to the pi I. I'll remind you guys, that's the cosine of pi plus I times the sine of pi. One of you is asking me what do you need to know for the course. You need to know everything about trigonometry that you ever learned and remember it. Okay? Trigonometry matters here quite a bit. Not knowing trigonometry will stop you dead in your tracks for some problems, okay? But mostly the basic trigonometry. The harder trigonometry we can actually derive. I have a homework problem like that, actually. I show you how you can derive a trigonometric identity using the imaginary exponential. Yep.
There it says w sub 2 equals e to the 2 pi. Is that over 2?
Yeah, that's 2.
So
Oh, you want me to write 2 the same way every time?
Well, isn't it 2 pi I over 2, so wouldn't that just be pi I?
Yeah. We don't disagree. We're on the same team. We're on team pi I.
Substitution. Oh, I'm not me. Yeah, I'm sorry. I was just. Okay.
Okay. All right. So, long story short, the second principal root of unity is -1, right? N equals 3. Omega sub 3 is e to the 2 pi I over 3, which is like cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. All right? So if I was so foolish as to try to graph that, here's my unit circle, right? Where is that in the unit circle? Well, 2 pi over 3, right? So that's like here-ish, right? Maybe. Did I do that right? Let me think about that for a second. How much beyond the y-axis is 2 pi over 3? 30 degrees. Oh, so it's more like up here, right? My bad. Don't tell don't tell Professor Young or any of the other people teaching pre-calculus I did that. It's very sad. Very sad. So here's omega 3. What happens when we calculate omega 3 squared? We get e to the 4 pi I over 3, right? Which is down here, right? Omega 3 squared. And what happens when we calculate omega 3 cubed? We get e to the 6 pi I over 3, also known as e to the 2 pi I, also known as 1. So, in fact, if we look at 1 to the 1/3 power, it contains 3 things. It contains 1, it contains the principal third root of unity, and it contains the principal third root of unity squared. The picture for my n equals 2 case I didn't make because it's kind of boring. Like, I can superpose it on this unit circle. What are the principal roots? What are the second principal? Excuse me. What are the second roots of unity? There's only 2 of them, right? Like this guy and this guy, right? 1 and -1. So like 1 to the 1/2 power is actually the set -1. Well, I'll put 1 first, all right? So I don't know, whatever. It doesn't matter which order. These are not ordered sets. I'm just a creature of indecision. Yes?
So it's almost like for whatever complex number you're taking the nth root of, you take your unit circle, you make the radius whatever the square root of the modulus is, or nth root of the modulus is.
Uh-huh.
And then you split the circle up into n pieces.
Yes. Yes.
And each point on those n pieces is your nth root of whatever.
Essentially that. So for the principal nth root of unity, you can just get from rotating 2 pi over n from the positive x-axis over. That's what it is. So for the fourth root of unity, the principal fourth root of unity is exactly just I. That's there. This is I. I squared is down here. I cubed is over here. I to the 4th is over here. So we've got, the fourth root of unity, the square of the fourth root of unity, the cube of the fourth root of unity, and of course the fourth root of unity to the 4th power. I think you see that there's a kind of obvious theorem here that I probably should have stated about 10 minutes ago, which is what? Is this a theorem? I don't know if this is really a theorem. This is more of like a theoremito. So here's a little tiny. No, it's a tiny theorem. It's tiny. Tiny theorem. So omega to the n power is equal to 1.
So what's the difference between a lemma and a tiny theorem?
Lemma you write in full-size font.
All right, that sounds.
Yeah. Okay, so it's a little bitty theorem. So these are the 4th roots of unity. What are the 5th roots of unity? You see where we're going, right? The 5th roots of unity, they're harder for me to draw because I got to figure out what's 360 degrees divided by 5. It's like 72. Yes, I think 72, which makes it like here, and then 140 is like over here-ish, and then like over here-ish, and then like over here-ish, and then back to here. Principal roots of unity always come in conjugate pairs. If there's a complex root of unity, it's got a conjugate pair somewhere in the list of powers. This will always happen. You've seen it in the examples. It always happens. The other thing that you can see is that if we take 1 plus omega n plus omega n squared, I'm not going to prove this. I'm just going to state it. Maybe I'll make this a homework problem. Plus omega to the n minus 1 power. You guys tell me, what's that equal to? We'll try it out for 2. What happens when you add them? 1 plus minus 1.
0.
What happens when you add the third roots of unity? See these two guys? This is actually minus 1/2 plus I root 3 over 2 in detail. This is actually minus 1/2 minus I root 3 over 2. Over 2.
Conjugate pairs will cancel each other when they're added together.
Not quite. All the conjugate pairs, imaginary parts, cancel when they're added together, and they leave you a residual real part whose sum over net of all the conjugate pairs nets to minus 1, which then cancels the 1. But yeah. Oh, I think I might have done your homework problem. But I'm not sure it's a homework problem. But the point is, the average of all the nth roots of unity is 0. That's pretty neat. I mean, I think it's pretty neat. Whatever. My point to you, I think I've done enough here that you can appreciate that while k over there on the middle board is an arbitrary integer, this isn't really an infinite list, right? Because what happens with this omega k to the n? It cycles back, right? After you get to the nth power, you're back to 1, right? So if we start at 0, and then we go 1, 2, 3, da da da, all the way up to, n minus 1, we have gotten all possible nth roots of unity. Indeed, this could be used to model modular arithmetic. There's a natural isomorphism between the multiplicative group of unities and addition modulo n. That is true. But since some people in here have not had Math 200, it feels somewhat wrong to say such a thing. And yet I have said it. My apologies. Do your homework. Doing your homework is where you find the course. I do say some things beyond what I test in here. Anyway, so there it is. So actually that's n, because 0 to n minus 1 is n things. And so lo and behold, this has a name. The principal nth root of z is equal to, the principal nth root of, good grief. I've gotten confused all of a sudden. Give me a second. The principal nth root of w, rather, is equal to the nth root of the modulus of w times e to the I arg w over n. This is a definition. So while there are n solutions to the equation w equals e to the n, this is a specific choice of one, which is called the principal nth root of w. All right? Now, with that notation, I can write down, basically here's the theorem, if you like. Or, I mean, if you wanted to, this could in principle serve as a definition of w to the 1 over n power. Anyway, it's true. It's the set which contains the nth root of w, and then omega sub n times the nth root. I regret using n and w here both. So sorry. What's done is done. But my w's are jagged, my omegas are not. So that's my defense. Omega sub n squared nth root of w. See, if we could turn back time, if we could find a way, we go back to the things that had hurt you, and I'd say that we should have just flipped z and w at the start of this discussion, and then we would have not had z and omega. We'd had z and omega. Anyway, whatever. All right, list of things to n minus 1. Anyway, there you go. This, my friends, is the set of principal, excuse me, not principal, this is the set of the nth roots of w. All you got to do to find them is you find first the principal nth root, and then all you got to do is power that thing, multiply it rather, by powers of the nth principal root of unity. That's how you calculate the set of nth roots of a complex number. Right? We could teach this to high schoolers. It's really not that complicated. If you have complex, in fact, it'd be easier for them after they'd just done trigonometry and it was all fresh on their mind, as opposed to you guys who have used trigonometry here and there, but not so much lately, right? You're like, I'm in the middle of physics, so shut up. You know? I don't know. I don't know what you guys are doing. Are we good? We should work an example, right? I personally like the fourth roots because it's just multiplication by I, so it's, it's really easy to think about. Let's see here. But I probably should do something ugly. I always regret doing something uglier. Let me just be lazy and not do that. Example 1. So let's say 1 plus I root 3, and let's calculate the fourth roots of this guy. So what's the first order of business? Maybe picture it, right? What's that number? 1 plus I root 3, so it's like here, right? So this distance is 1. This distance is the square root of 3. What's this distance? How far is that? What's the magnitude of that? 2? Okay, cool. So what's that make this angle here? So like, let's see here. Apparently, cosine of theta is equal to, what, 1 over 2? So anyway, yeah, somebody was saying something about like remembering that circle of values. You do have a scientific calculator in here, so you can figure things out, right? But if you already have them memorized, then that will speed things up, right? But whatever. This is pi over 3, right? Agree? Pi over 3. So this apparently is 2 times e to the, well, pi I over 3. We're trying to find the fourth roots of this guy. So first order of business, let us calculate the principal fourth root of this number, you know. Okay, so that is the principal, well, that's just the plain old fourth root of 2, right? And that'll just, whatever that is, it is. And then what? And then we have e to the I. So the argument here is pi over 3. So we do pi over 3 divided by what? Well, we're calculating fourth roots divided by 4, right? In other words, the principal fourth root is just the fourth root of 2 times e to the pi I over 12. There you go. All right, and then what? Well, if we want to calculate the whole set of fourth roots of 1 plus I root 3, now we can. We just list them out here, right? So we've got the fourth root of 2. I'm going to get really tired of writing that, but here it is, e to the pi I over 12, right? Then I take that and I multiply by omega sub 4, right? Now remember, omega sub 4 is equal to I, but we could also look at it as e to the 2 pi over 2 times I, right? Now I think that for this problem, I would like to look at omega sub 4 as equal to e to the, I don't know, 6 pi I over 12. That would probably be a better way to look at it, because then I can do the arithmetic, right? So when I look at this times omega sub 4, what do I get? Fourth root of 2 e to the 6 plus 1, 7 pi I over 12. and then I multiply by omega sub 4 squared, and I get the 4th root of 2 times e to the, I need to add 6 again, so 13 pi I over 12. And then I multiply by I again, add another 13, what have I got? 4th root of 2 times e to the, add 6 to 13, 19 pi I over 12. That's 4 things, right? Once you get the 4 things, you're done. 1, 2, 3, 4. Now, I've written these in polar form to help make the graphing that I'm about to do obvious. But let me just take a step back here and tell you what I just did. So suppose I didn't burden you with writing the answers in polar form. What if I just said find the 4th roots of this number? You would be completely within your rights not to do this stuff, which is kind of a little bit complicated, but instead just write down, well, I times, the 4th root of 2, e to the pi I over 12, right? And this right here is just minus the 4th root of 2 times e to the pi I over 12. And this over here is just minus I times, the 4th root of 2 times e to the pi I over 12. That's all this is. We're multiplying by I squared, I cubed. Graphically, what's going on here is the first solution, right, is where it's at pi over 12 radians, which is like, I don't know. Somebody want to tell me? 15 degrees? Oh, that's right, yeah, because 30 degrees, half. So it's about here, right? That's and I'm going to go back to, that's the 4th root, a principal 4th root of 1 plus I root 3 is right there, right? And then you're up to 7 pi over 12, so that's kind of like here. And then the next one is like here, and the last one is like here. Those are where those numbers are. They're symmetrically situated around the origin. And you can kind of see that if you were to add the nth roots of a complex number, they're going to add to 0, right? That's not something that only happens for 1. It looks like that probably happens for any complex number, but it's kind of a more complicated reason for an arbitrary complex number. You can just see it for the nth roots of unity better, but here I'm arguing by symmetry that these sum to 0, which is just a fancy way of me saying I'm waving my hands and you can see it. Any questions? Yep.
Notation-wise, when you're using the actual roots symbol, is that meaning you're looking for the principal root, and then when you're showing it raised to the quarter power?
So our custom.
Does that imply that that's
Our,
looking for all roots of the principal?
so our custom is that if we write the nth root of a real number, all right, then that means the nth root of a real number in the sense that you learned before this course. It is an element of the reals. Not just that, it's an element of the positive reals.
And it's a unique element.
Yeah, there is a unique solution to, something raised to the nth power equal to a positive number. There's one in one solution to that. So here's the rub, is that we do not use the notation. You simply do not use the notation real number to the 1 over n for that in this course. This, to quote my community college professor, dog will not hunt. I mean, you can't do that because we have given this a technical and different meaning than you just freely interchange the square root of x and x to the 1/2 in pre-calculus, right? We drill that into you, in fact. Now I'm trying to remove that from your, do not do that. Let me show you why. You're like, well, why? Why can't we have nice things? Well, let me show you over here. 1 is equal to -1 squared, right? Which is equal to what? like, oh man, I've forgotten how to be confused. Give me a second here. I gotta look it up. Where's that pesky calculation? I usually can remember this thing. Well, I was talking to Ernesto earlier. This is about the time in the previous lecture I got stumped, isn't it? Yeah. All right. 1 is equal to, well, yeah, that's not what, I went the wrong way. It's equal to minus I squared, right? Which is equal to minus, I times I, I believe. And then, let's see, what do I want to do? So that's the square root of minus 1. Square root of minus 1 times the square root of minus 1, right? And then, well, that's minus the square root of minus 1 squared, right? Which is the square root of 1 with a minus outside, right? Which then is minus 1. So there's a problem if we're not careful about the notation. Yeah.
Isn't the error there in the first, third, fourth equality?
Right here. Well, yeah. Yeah.
No, the one immediately before that.
Oh, no, that's just notation. I is the square root of minus 1. I mean, I is the principal root of minus 1. That's not wrong.
Yeah. I mean, at that equality.
The principal root of minus 1 is the square root of the modulus of minus 1 times e to the I arg of minus 1 over 2. But that is, the square root of 1 times e to the I. What's the argument of minus 1? Here's minus 1, right? What's the angle there?
Pi.
It's pi. So that's e to the pi over 2, which is equal to I. So indeed, the principal root of minus 1 is I, which is good.
I'm more just saying the negative 1 is under that square root. If you're using the real square root, which you had sort of talked about earlier, negative 1 wouldn't be defined because...
But I'm not using the real square root. I'm using the principal square root of a complex number, which is defined as such. So the problem is actually this equality right here. It's just not true. The laws of exponents don't work for the principal square root, unless the numbers that you're applying to it fit in such a context as to maintain the law. What I can tell you is that, minus 1 and 1 are both elements of minus 1 to the 1/2. That's why we're getting 1 and minus 1 here, because they're both second roots of unity. So if you're going to use that equality in the middle that I pointed an arrow to, you can't think about single element. You have to think about sets of elements if you're going to use those laws. So you're back to the whole multiply valued problem. If you're just going to nonchalantly use laws of algebra. You can't use laws of algebra here unless you know what you're doing. Yeah.
Why don't the usual...
Well, that sounds like a homework problem. So, yes. I'll make a problem in the next homework set to explore that. It's a good question. All right, so any other questions? The answer has to do with when you add the arguments, you don't have to end up still in like the same angle that you're supposed to be in, something like that. But yeah, yep.
Something just like math outside of that. Why did we increment by 6 pi over 12? For the
Oh, because I'm adding, I'm multiplying. Because I'm up against like e to the pi I over 12 to start with, right? And then I'm multiplying it by omega sub 4 to some power, right? And so, but what omega sub 4 is e to the, if I make it e to the, 6 pi I over 12, when I multiply these, I can just add the fractions. If I didn't make the common denominator match, then I wouldn't. It's just to make the fraction adding easier. That's all. You could have left it as pi I over 2 and then just did like, 1/12 plus a half, and then 1/12 plus a half plus a half, and then 1/12 plus a half plus a half plus a half. You get the same thing. Question? No? Okay. So that's principal nth root. Now, I should probably do one other thing with this before I go on, but I definitely should go on. Otherwise, I'll regret my life. I mean, that's not true. Well, it's partly true. With regard to this lecture, I'll regret my life because I want to get to a certain spot today, and we're not there yet. And of course, like, this stuff is really cool, and you can easily just spend hours on it. But the other thing I should mention here is if I was going to say, oh, I don't know, calculate z to the 4th, minus 1 plus I root 3. Well, if I was going to set that equal to 0, first of all, these are the solutions of that being set equal to 0, right? But, hey, we can factor this, right? Because this is actually going to be z minus the 4th root of, I'm tired of writing this number. Let me call this thing, I don't know, alpha. Alpha. And then you've got z minus I times the 4th root of alpha. Z minus, well, I squared is just plus, right? 4th root of alpha. And then z plus I times the 4th root, principal 4th root of alpha. So you can use these things to factor polynomials, right? Because the factor theorem is still true here, guys. If f of z is a polynomial over the complex numbers, then f of c equals to 0 if and only if z minus c is factor of f of z. So, if my f of z is equal to z to the 4th minus 1 plus, and there's something wrong here, right? Which is what? This is a sin of omission, not commission, but nevertheless exceedingly sinful, because there must be a parenthesis here. Otherwise, it's just not true. All right? So z minus 1, parentheses plus I root 3, if I set that equal to 0, that's the same as what? Z to the 4th equals to 1 plus I root 3, right? Which is to say that z is an element of what? The 4th root of 1, the 4th root of 1 plus I root 3. But we know what those are. We just calculated them in the last example. Those are exactly the zeros of this polynomial. And by golly, if you've got 4 zeros of a 4th order polynomial, you've factored it. Because you can't have 5 zeros for a 4th order polynomial. Like, you multiply them out, you get z to the 5th. That'd be bad, right? So the bad news is the pre-calculus algebra involving roots, we have to be really careful about that. The good news is the polynomial stuff gets better. And we can factor things that we wouldn't have even dared to even think about factoring in high school with this technology. All right? Okay, so that's all I got to say about that for the moment. Let us move on here. I have other functions to talk about today. And that actually kind of brings me to my next, what's the word? Story arc, I suppose, which is chapter 2. We're in chapter 2 now. And so I'm going to try to hit the high points here and resist the urge I have to tell you everything about everything. because we really just need the definition and some basic ideas to get the discussion started for now. So I want to talk about complex functions. Complex functions. So we have some standard notation, vernacular if you like. F is a mapping from, let's say, D, a subset of the complexes to the complexes. So here I would say D is equal to the domain of F, right? So that's one obvious question. What's the domain of the complex function, right? That's one thing. Now, as a matter of notation, we have f of z is equal to u of z plus I times v of z, or aka f equals to u plus iv. This is the real component of f, and this is the imaginary component of f. So every complex function can be broken into a pair of real valued functions, the real part and the imaginary part. Yes, sir?
For example 2, you have alternating i's, like each time you multiply alpha by an I. Is that because those are the components of omega sub 4?
Yeah, omega sub 4 is equal to I, right? I just, the reason I wrote it that way, Jeff, is because I didn't want to write all those fractions again, because I would copy one of them down wrong. But you could just use those fractions I've just erased and put them there. You've got half a dozen different notations you could use to express these numbers, but
I just wanted to
yeah.
make sure that was all.
Yeah, you're right. So one obvious question with a complex function is what's its real and imaginary parts? We use u and v as our standard notation for this, all right? Just like we use x and y for the standard notation for the real and imaginary part of a complex variable, all right? That's it. Obvious other question is, what's the modulus of f of z? Like, this is an interesting question to ask for a given function. How big is the value of the function as the output, right? So if this is the formula for z, can you guys tell me what the modulus would be? It would be what? Just the square root of u squared plus v squared, right? And technically, so I sometimes write the of z and I sometimes don't, and whatever. It's like the old, do you write f or f of x? Now, if you write an answer on the Math Stack Exchange, or especially Math Educator Stack Exchange, there is a subset of professors there who will berate you for confusing the idea of function and function value. And they're not wrong, but I just don't care. So I almost never use this formula. It's almost always better to find the modulus of a complex function by some other direct argument. All right. In fact, using this way of thinking to find the modulus of the complex function's value might be the worst way. All right. Now, I should also mention, of course, that the range of f is what? This should come of no surprise to you. That is f of d. It is the image of the domain, all the output values. All right. Then, past these initial kind of basic sets of questions, there are deeper questions like, geometrically, what's going on? What is this function? What's it doing? How do we describe it? Now, you've been immersed in real calculus, so you have an idea about how to visualize a function. You do what? You look at its graph. We can't do that, because if we have w equals to f of z, right? This is what we think about w equals to f of z. Well, we can't graph that, because w is two-dimensional and z is two-dimensional. So you have 2 dimensions for the domain. You got 2 dimensions for the range. That's 4 dimensions, which is one too many for pictures, right? At least for me. So what we do instead is we look at the function as what's called a mapping. So you take and you draw the domain and you draw the range, or rather the codomain. So this is this is the codomain. The codomain is the set of all possible output values. That's different than the range. The range is the actual values which are attained. This is the difference. So the codomain is the whole complex plane. The range is what it actually hits. And then you just, you study, if I have z here, and I've got w equals to f of z over here, you say what happens to things as you map them from here to here. You do things like, if I have a horizontal line here, what happens to it under the mapping? Where does it go? I got a vertical line here. What happens under the mapping? Where does it go? I've got a circle here. I send it under the mapping. Where does it go? We study how objects in the z-plane are mapped to the w-plane to understand the geometry of a complex function. All right? That's an interesting question for a given function, and it takes time and careful analysis to fully grasp that. All right? That's a deeper question. A deeper question still is f invertible? Does it have an inverse? If not, how can we restrict the domain to make f restricted to u injective? Now, injective is just another word for one-to-one. That's the necessary and sufficient condition to make the function invertible. The restriction, rather. Yes, sir?
Don't we have to deal with the function not being well defined in the first place? Because we've already demonstrated that doing some sort of operation like...
Well, yes, at the start of everything, we should make sure our function's well defined. Yeah, of course. So, for example, I asked for an example number earlier, and somebody told me E. Nerds, right? So EE. That's what I did. I think it was between examples 2 and 3, so it was okay, EA. I guess for us, there we go. This example is going to be very complex, but sorry. Ruh-roh.
You're not.
Sorry, whenever I start laughing at that, it makes me think of the old Jeopardy with Sean Connery. Oh, it gives me joy. But anyway, your mother, Trebek. Let's see here. You guys know what I'm talking about? No. If you don't, it's fine. So this would not be a function for the reasons that you're worrying about, because of course this is equal to a set, namely the square root of z, the principal square root, and minus the principal square root. So to answer your question, you asked me before class, Ernesto, how would you solve that quadratic equation? The answer is you'd use the principal square root. Well, you'd use the fact that when you solve a complex thing squared, what are the solutions? The solutions are plus or minus the principal square root. It's not plus or minus the square root anymore, it's plus or minus the principal square root, which takes care of how you, if you have got, taking the square root of a complex number, it gives you a specific choice of that square root. Okay. But yes, this is not a complex function. This is multiply valued. All right? So not a function.
So if anything, it's a complex mapping.
No, I wouldn't say that either. Mapping still means function. All right, so example, I don't know. 27? All right. Why not? That way if I need to add another lecture later, I've got a lot of numbers to use. All right, so actually, let's not do examples. Oh, one easy example. One easy example. F of z, let's just do something really easy here just to keep it mellow. Z cubed. Let's find the real, oh man, I hope this isn't one of your homework problems. See, this is the danger, is I'm a creature of habit, so if I make up problems off the top of my head for your homework like I did, and then I'm giving a lecture without having stuff written out and having looked at your homework, there's a high probability I end up doing some of your homework problems. What's that?
See the fifth is definitely
Huh. All right, so this right here, the binomial theorem is still true. All right? The binomial theorem holds in the complex domain. So we can write x cubed. The binomial theorem goes like this, right? 1, 1, 1, 1, 2, 1, 3, 3, 1, and so forth. So the binomial coefficients are 1, 3, 3, 3, 1. So I do x cubed plus 3 x squared times iy plus 3 times x powers down, iy powers up, and then plus iy cubed, right? And then simplifying that, we've got x cubed minus 3xy plus I times 3x squared y minus y cubed, I believe. All right? Yes, sir.
But wouldn't c to the 1/2 be a mapping in like the abstract algebraic sense, where it's not well defined, but it still describes a set or a subset of A cross B, where for all A and A there exists a B and B?
I don't think so. No. I don't define mapping like that. So I always think about it not in terms of, I don't think about subset of Cartesian product. For me, mapping is always from set to set. I don't think about like the subset of the Cartesian product. But anyway, we can talk more in office hours. Yeah.
Is that negative 3xy squared?
I was about to say, we should see that every term here is of degree 3. So your question is a good one. Because that should be what?
XY squared.
Thank you. Yes, sir. You are correct. Now this, my friends, is u, and this is v. Hooray, we've calculated our first component functions for this complex, the complex cube function. That's u, that's v. What's the magnitude? What's the modulus of this function? So the wrong way to do this, right, would be to take these and square them and add the square root, right? There's a simpler way. See, because this is the modulus of z cubed, right? So it pays to go back to complex notation. Don't be fished into my formula. Use this instead, and then that is, well, the modulus of z cubed. In other words, the formula for the modulus is the square root of x squared plus y squared. You know, we could write that all to the, well, I guess I better write it like this, huh? I better not write to the 3/2 power. I guess we should allow ourselves to write to the 3/2 power here. Why? Why is there no danger for confusion? Well, a reasonable amount of danger for confusion, let's say that. Because we're taking the 3/2 power of a real quantity, we agree that means the regular 3/2 power. All right?
Because
Right.
we know it won't be multi-valent.
Yeah. And so there you go. This function can be as big as it wants to be, right? Okay, anyway. Let me go on. So there are really 4 examples I should share with you today. And we'll be working with these as we go on. So I have no regrets. Like, I think it's more important to go slow on the nth roots, because I think the nth roots idea is actually more complicated than these things I'm about to show you. The things I'm about to show you actually, they make wonderful examples. The lion's share of my examples is built from these 4 things, all right? But they're actually pretty harmless. So here's the definition. Complex exponential. E to the z, in other words, e to the x plus iy is equal e to the x times e to the iy. I guess I'm not to the definition yet. The definition here it is, e to the x cosine y plus I e to the x sine y. There you go. That's the definition for the moment of the complex exponential. Again, we will find a way to supplant that with a more primitive analysis-based definition eventually, but this is a good transitory definition for us to work with as to have nice examples. You see what this is? So what's the real and imaginary part? So you see u, e to the x cosine y, v, e to the x sine y. And of course, this is consistent with our introduction of the